Hello everyone, and welcome to sdns2021. My name is Frank Denis, and today is a little bit of a special day. It's not a very common thing to celebrate the anniversary of a network protocol. However, it's always great to meet people and discuss interesting topics. In the past decade, there's been a lot of activity around the DNS protocol, and all of that wasn't really about performance anymore. For the first time, it was about privacy. The general public became aware that DNS, which is one of the foundations of the internet, was not really secure. And more importantly, that it was used for data collection and censorship. New protocols were designed, new tools, and it became a common thing to not use your ISP's resolver anymore. New ideas emerged, such as DNS over blockchain. We're still in the middle of a transformation, but we already have a big community of people actively contributing to this transformation. And this is what I wanted to celebrate today. Just a couple of weeks ago, there was absolutely no plans at all to organize such an event. So everything was organized a little bit at the very last minute. However, we have a great lineup of speakers. We have great, nice, and diverse attendees. So I want to say a big thank you to all of you who made this possible. Also, a shout out to Loris from the Zig Software Foundation, who gave me a 101 crash course on how to use OBS for live streaming. This is something I have never done before, so if there is no sound, if the image is blurry, if you see puppies or cat pictures instead of presentation slides, please tell me and I'll try to find the right button to fix it. And now some logistic details. First, we have a Discord server, and this is how you can connect to it if you're not already. You can also find the link in the description of this video. After connecting, you can chat with everybody else. We already have a bunch of conversations going. You can chat with a keyboard or even with your voice. We have voice channels. And there's a channel named Questions. This is a very important one. If you have questions about the presentations, this is where you should ask them. After a presentation, some of these questions will be read aloud and answered by the speaker. The remaining questions are not lost, because speakers can also use Discord, read them, and answer them directly on the channel. After the presentation will be done, you will have the opportunity to talk about anything you want for 90 seconds. These are the lightning talks. And anybody can present, but only 90 seconds. If you want to show and tell some software you've been working on, if you just want to say hi, if you want to play some live music, tell a joke, whatever, feel free to do so. If it's somehow related to DNS and or privacy, it's better, but it doesn't have to. Instead of a 90-second presentation, maybe you want to privately discuss some topic with a small group of people, like show how to set up a DNS server, or how to configure something on Android. What you can do is submit your ideas in a channel called Proposals. And new channels will be created specifically to discuss each of these topics. And a discussion channel also supports screen sharing if you ever need that. So, during the presentations, try to think about what you could present in 90 seconds at the end. Or if you want a specific topic to be discussed with a small group of people. Cool? All right. So now let's talk about DNS again, and more specifically about DNS scripts beyond the protocol. But of course, we have to start with DNS.
DNS is not the phone book of the internet, because nobody is using a phone book anymore. What DNS really is a large, decentralized key-value store, which was designed about 38 years ago. And I keep being impressed because it still works, it still scales really well, even though the original design hasn't changed much. The way to send a query and receive a response is still the same as 38 years ago. To be honest, this is slowly changing, but it was 100% the case 10 years ago. And the key of this incredible scalability is the simplicity of the network protocol. At application level, well, it's a mess. But if we just look at the transport, it's very simple and efficient. One query gets one response. This is like sending postcards. The address of the recipient is written on the postcard as well as the question. And then we don't have to care about what happens next. All we know is that eventually it will reach the recipient. And the recipient responds the same way with the postcard. We just described UDP protocol, which is a perfect fit for DNS. Besides being simple and stateless, once a postcard has been sent, we don't have to track it. This system has other advantages. In particular, if one of these postcards is lost or delayed, it's not going to delay anything else. So we get great latency guarantees. And this is why this exact system is also widely used by online games. There are a few problems though. First, anybody can send a postcard that says, please respond to that address, even though this is not their address. So a random target can receive junk they never asked for. Another problem is that if a response is too long to fit on a postcard, it has to be split into multiple postcards. But if a message is split into multiple postcards, it's possible that during transport, someone replaces one of the postcards with a different one and totally changes the meaning of the message. This is why, occasionally, DNS can use TCP. Instead of sending postcards, TCP is more like constructing a single lane road on which things can move, sequentially one after the other. Both mechanisms and the way to switch from the former to the latter are very well defined and supported by the vast majority of DNS software. Problem is that there is no encryption whatsoever. Anybody on the route can look at the queries and at the responses. They can also replace them with something else. This is typically how people use DNS. On any of these links, it's possible to spy on and tamper with the data. If you're connected to a public Wi-Fi access point, well, then the router can see all your DNS traffic, but can also modify it. If the router is trusted, then the ISP may not, and this is a very common case. DNS remains the fastest, easiest, and cheapest way to do surveillance and censorship. So, a partial solution is DNSSEC. DNSSEC ensures that when a response is received, it matches what the domain name or zone owner configured. However, there is no confidentiality. DNSSEC still assumes that DNS data is public. This requires everything in the chain to support and have been configured for DNSSEC. DNSSEC is not a switch you flip and poof, everything is more secure. You can flip it, sure, but most of the time it's not going to do anything. Even Google domain names don't support DNSSEC yet. Finally, when it's useful, the value of DNSSEC stops at the resolver. So here, the ISP and the router can still do whatever they want. So, in 2011, I made a quick experiment. What if we don't change anything to the way DNS works? We will let it use UDP and TCP exactly the same way as before. We don't change anything to the queries and responses. We take them unmodified, but we encrypt them. There you have it. This is DNSCrypt, and it was made to secure everything on the left. This is how a plain old DNS packet looks like. We're just going to replace the data with an encrypted version of it. We don't change the data at all. We don't even need to parse it. The only thing we do is add some padding after the data. This is just some extra bytes to hide the real size of this data. And we prepend a random number. This is a nonce. One of its purposes is that if we encrypt the same thing twice, we get totally different outputs. We also include a public key, which is used by the server to know how to encrypt the response. There are no sessions, no state. The client can choose to switch to a different key whenever it wants, and even use a unique key for every single query. Also, TCP connections are not reused. That way, if we route DNSCrypt over Tor or any other proxy in order to hide the client IP address, there's no way for a server to know that two queries were made by the same person or device. So, that's it. The protocol is very simple, very lightweight, very fast, and it requires minimal changes to existing DNS code. And now, it's impossible to change the data, even if it's sent as multiple fragments. Of course, only the client and the resolver can decrypt the data, and fake responses will be detected right away. By default, DNSCrypt uses the same port as web servers, 4 port 3. and it's possible to run both a web server and a DNSCrypt server on the same port and IP address. So it's easy to deploy. A DNSCrypt server can be hidden behind a regular HTTPS server. Shortly after the first implementations were made, individuals, organizations, and companies started to either add DNSCrypt support to their existing resolvers or set up new, free public resolvers specifically for this. Pioneers were CloudNS Australia, OpenDNS, servers from the OpenNIC network, and Soltysiak, that since became DNSCrypt Poland. Within a year, I think we had about 30 public DNSCrypt servers to choose from. Commercial products, such as Dome Shield from Komodo, started using it, and still do today. Big corporations, such as Yandex, also set up public DNSCrypt servers. People started to write new tools in order to use it, for Mac, for Windows, for routers, for mobile devices, which was awesome. Simple DNSCrypt, in particular, was a fantastic contribution for Windows users. Not to mention integration in DNSDist, Unbound, and there was even an implementation as a Linux kernel model. So there was a protocol, but more importantly, ways to use it on any platform by anyone. In 2016, the first web browser with encrypted DNS was released. That was the Yandex web browser with built-in support for DNSCrypt. For the project, it was pretty clear from the beginning that improving DNS privacy was not just about encrypting DNS traffic. First, it's about having privacy-respecting resolvers, and virtually all the DNSCrypt resolvers made a public claim that they don't store logs, which was something new. Then, it's about allowing users to understand and control their DNS traffic. For example, the DNS implementations could show query logs in a very simple way so that people can spot application falling home. They also had really good support for filtering. People were able to decide what DNS traffic was allowed to go in and out. We started to see public block lists for DNS. Implementations quickly added support for Tor so that client IP addresses could be hidden. All these things were not directly part of the protocol itself. However, they were part of the expectations of DNSCrypt users and contributors, so they were fully supported and encouraged. At that time, on iPhone, using a custom DNS client application was believed to be an impossible task to do without a jailbreak. But in 2017, the first encrypted DNS client application for non-jailbroken iPhones was released on the App Store, DNSCloak, a port of DNSCrypt proxy to iOS. And this is still one of the best DNS applications on a mobile device today. Shortly after, version 2 of the DNSCrypt proxy client was announced. It was a new start. It was a rewrite from scratch made to support all the things people had been asking for. All sorts of filtering, cloaking, logging, proxying, but also it was ready to support more protocols. That made it pretty clear that the mission of the DNSCrypt project was not just to define a protocol, but to improve and support practical DNS privacy at large. Around the same time, some smart people started to work on a document describing how DNS could be done over HTTPS. And that made sense. HTTP sounds like a terrible fit for DNS. When Google made something similar before, everybody thought it was a joke. But HTTP has become the way to transfer data over the internet. Any kind of data, large and small, and not just websites. HTTP is constantly being improved. HTTP is being deployed everywhere. CDNs know how to cache and distribute HTTP content. So why not reuse that for DNS? And there it is, you get DO. DO is not about being difficult to block. It's actually really easy to block right now. It's about reusing everything we already have today for HTTP. On February 2018, DNSCrypt proxy got support for DO. We set up the first globally distributed public DO server. The code for it was made public, so anyone could also run a DO server. DO was still a draft at that time, but every time there was a change, both DNSCrypt proxy and the server were brought up to date the same day. And unsurprisingly, when the final version of the DO specification was published, we were more than ready. We had everything tested, deployed, and already had quite a few DO users. It was surprising to read that the first implementations and deployments of DO were made by the DNSCloak project. But the purpose of the project has always been about improving DNS privacy by all means, not just being focused on one protocol. All the DNS encryption protocols still had a major issues. Resolvers were seeing all the client IP addresses, and even with a no-log policy, that didn't make people comfortable. Encrypted DNS is not enough, and I make the claim that it already belongs to the past. What we need now is to make DNS anonymous, something we had already solved by allowing DNSCrypt to be used over Tor, but people were concerned about the increased latency. The same way DNSCrypt was designed, can we make something simple, fast, built upon what already exists with minimal changes? So, in 2019, we announced the anonymized DNSCrypt protocol and its client and server implementations. This is done by introducing a new component called a DNS relay, which forwards encrypted data between a client and a resolver. In this setup, the resolver doesn't see the actual client IP address, only the relay address. And because the data is encrypted with a key that only the client and the resolver know, the relay doesn't learn anything about the data being forwarded. This is a very simple extension to the existing DNSCrypt protocol with minimal overhead. It's also safe and easy to deploy. If we take a look at a well-known list of public encrypted DNS resolvers today, this is what we have. All these servers are up and running today. They are everywhere on the planet and they get an increasing amount of traffic. We should be really thankful to so many folks, especially individuals and organizations giving their time and knowledge to operate public servers just for the sake of improving other people's privacy. And all these efforts are useful, even to people working on other protocols. Do people care about DNS privacy? Is anonymized DNS, not specifically DNSCrypt, practical? Is it something people would use? The DNSCrypt community already has answers to these questions. So, today is not the celebration of 10 years of a protocol. It's 10 years of a growing community, 10 years of users enjoying more privacy and having better understanding of DNS. So, thank you to everyone. Thank you for contributing to making the internet a better, safer place. Once again, thank you.